Hey Science 30s, and welcome to topic 2.2 of Unit B, alcohols, carboxylic acids, and esters. Now, over the last couple of videos, we've been discussing organic molecules, organic chemistry. We started with a look at aromatics, which are cyclical hydrocarbons. We then moved on to chained hydrocarbons, which would be your alkanes, alkenes, alkynes. And then we began a discussion in our last video about hydrocarbons that have functional groups on them. And the first group that we discussed were the halogenated hydrocarbons, where you had functional groups that were basically halogens, either chlorine, bromine, fluorine, or iodine. Today, I want to discuss the other three functional groups that you should be familiar with in Science 30 as it pertains to hydrocarbons and organic molecules. And those are going to be alcohols, carboxylic acids, and esters. As always, with this unit, go to your data booklet, page 9. All the information you need is there. Looking particularly right about over in here on the sheet that has your generic formulas for those three types of organic molecules. I'll discuss what makes an alcohol, carboxylic acid, an ester, an ester. We'll get to all of that here today. And of course, naming conventions for all of them. Could you identify one if you see one? If you were given the name of one, could you actually draw it in a diagram? There'll be plenty of examples here to practice on today, and then some questions to work on to kind of test your knowledge on how well you know nomenclature for each of these three groups. Let's get started with alcohols. Alcohols, which are probably the most familiar of the three. Most people know, alcohol. It's out there. Go to the liquor store. I mean, that's when we think of alcohol, that's what we think of. But there's a lot of other types of alcohol out there, and they have multiple purposes, as we'll get to in a couple of seconds. What makes an alcohol an alcohol? Well, you basically have an alkane, you have an alkene or an alkyne, and you're going to add a specific functional group to that. In this case, the functional group is going to be a hydroxyl group. You know it better as a hydroxide ion, but it's not really an ion now because it's connected to an organic molecule, so we call it a hydroxyl group, which is that OH. In this case, the R refers to the alkane, the alkene, or the alkyne that the OH group is attached to, and that's basically the generic formula for an alcohol. How do you name it? So let's say, for example, I had this over here. Let's go with our magic number here. Carbon is going to have 4 molecules attached to, 4 bonding sites attached to the carbon. I've got 1 carbon, and one of those attached groups is going to be a hydroxyl group. Well, if I know it's a hydroxyl group, I know this is an alcohol. This would normally be, if this was just H over here, that would be methane. Because there's an O in there now, because we have that OH, that hydroxyl group in there, we're going to change the name methane to methanol. So that's basically all you have to do, is you have to count. The naming conventions for the alkane, the alkene, and the alkyne are the same. You just have to basically figure out how long the longest chain is in the alkane, alkene, or alkyne, and then you basically just change the name from ane, ene, or ine to anol, enol, or inol. Give you a couple of examples right here. Let's take a look. Oh, and by the way, the side chain, the hydroxyl side chain, takes precedence. So when you're numbering the molecule, when you're numbering your carbons, like we talked about with alkenes, alkenes, and alkynes, when we number the carbons, we want the hydroxyl group to have the lowest possible number. So in that way, it's sort of like what we discussed with alkenes and alkynes, where the double bond took priority over any side chains that might be on the molecule. And I will give some examples that play all of this out here today, so fret not. We will go through all of this. Here's an example of an alcohol. How do I know it's an alcohol? Well, I see a hydroxyl group there. So I know I've got some kind of an alcohol. How do I name it? Well, as per usual, I got to name my longest chain, or number my longest chain. 1, 2, 3, 4, 5. It doesn't matter which way I number this one, because if I go from 1, 2, 3, 4, 5, or I go 1, 2, 3, 4, 5, that hydroxyl group is still going to be at the 3 position. So in this case, it doesn't matter which way I number from. If that was over here, then obviously I'd have to number from this side to give it a lower number than if I counted from that side. But in this case, it doesn't matter which way I count from. I'm going to get the hydroxyl group in the third position. I've got a 5-carbon chain, no double bonds by the look of it on this skeletal formula, so I know I've got pentane. I've got a pentane molecule there. But because I've got the hydroxyl group, I'm not going to name it pentane, I'm going to name it pentanol. And just like with an alkene or an alkyne, where I had to give the number of the carbon that the double or triple bond was attached to, in this case, I have to indicate where the hydroxyl group is. So in this case, it's on carbon number 3. So I'm going to name that penta-3-ol. That's how you would name it. Everything I've just discussed there is on that slide. You can kind of check through the notes there just to make sure that I didn't trick you, but that's pretty much how you would name that one. You can't just call it pentanol, because you could have, in theory, there could be 3-pentanol, which is that. If I put that hydroxyl group here, that's going to be a different structure. So that's going to be penta-2-ol, pentane-2-ol. And if the hydroxyl group was at the end, well, now that would be pentane-1-ol. So it does make a difference where that hydroxyl group is in the naming of the molecule. All right? Let's give you another couple of examples here. If I can advance the slide. Apparently my Siri is basically stuck on my screen right now. How lovely. Siri, I'm going to wake you up. There we go. Siri's always listening in these lessons. Let's try that again. Here's another example of one. This molecule has a bit of a change to it, though. This one it looks similar to the last one I just drew, except my hydroxyl group now is on the main chain. What you'll notice now is I also have a side chain. So now not only do I have a functional group now, but I've also got a hydrocarbon side chain on this sucker. So I'm going to go 1, 2, 3, 4, 5. I think is what that diagram was. Yep, we got one side chain there, and we got a hydroxyl group there. Now, when I see this diagram, I do not now count this as a carbon, because that essentially is my hydroxyl group. That is my hydroxyl group that is attached here. Because I've indicated that there is a hydroxyl group here, that I know now that that is actually, it is like a side chain off the last carbon. So that is the only thing you have to kind of keep in mind when you're looking at these functional groups, is when you're looking at alkanes, alkenes, and alkynes, that would have been counted as a carbon over there. But because now we've got that bond that is attached to this hydroxyl group, it's implied that there is no carbon there. The last carbon would be there. So what I'm looking at here is a 4-carbon main chain. Again, longest main chain, 1, 2, 3, 4, or 1, 2, 3, or I can't really count it here because then that puts this hydroxyl group off the main chain. The hydroxyl group I want to keep on the main chain. So what I've got here is, and it's all single bonds, so I know it's going to be a butane. It's butane, but because I got the hydroxyl group, I've got a butanol. And because the hydroxyl group is on the first carbon, that is going to be butan-1-ol. That names my main chain, but I still have to name my side chain. There is a 1-carbon side chain there, and it's at the second position. Remember, we are giving priority to numbering for the hydroxyl group, so we definitely have to count from this side, regardless of where that side chain is. So that's going to be position 2 for that methyl group, because it is a 1-carbon methyl group. So that is going to become 2-methyl butan-1-ol. That would be the name of that molecule, and as I've just shown you there, it's all there. Read it up. If I didn't make sense in the video, the instructions are all there, showing you what the actual approach was to actually naming that molecule. But as you'll notice, this name here and the name that's in the notes, they match. I wasn't looking. I was just going by, good organic chemistry naming conventions. All right, and there is one more scenario. What happens if you've got an alcohol that has more than one hydroxyl functional group, which is the example you see on the page over here. I've got 1, 2, 3, 4, 5. So I got 1, 2, 3, 4, 5. That's my hydroxyl group there. And I've got a hydroxyl group here. So I've got 2 hydroxyl groups. Again, this is not a carbon here. That's my last carbon. There's a carbon. There's a carbon. There's a carbon. So I've got a 4 carbon main chain. So this is going to be a butane molecule. Again, no double bonds are indicated. So I don't have a butene or a butine because it's not a double or a triple bond. Now I have to figure out which way I'm going to count from. Again, I want my hydroxyl groups to have the lowest possible number. I could count 1, 2, 3, 4, or I could count 1, 2, 3, 4. This would be 2, 4 as opposed to 1, 3. I want it to be 1, 3 because that's where my 2 hydroxyl groups are, smallest numbers to the hydroxyl groups. I've got 2 of them. So you know I'm going to have to use a prefix, right? I can't just call this butane. Again, the main chain would be butane. So I couldn't just call this buta 1,3-all. That isn't going to work. Because what I haven't indicated is the fact, well, I kind of have indicated that there are two in there. But because whenever I have multiple side chains, we talked about this with alkenes, alkenes, and alkynes, I have to use my molecular prefixes, mono, di, tri, tetra. So I've got 2 of them. So in this case, I have to indicate that I've got 2 hydroxyl groups. So in this case, the molecule is going to be named butane 1,3-diol. All right. So I have to indicate the numbers of where the hydroxyl groups are, as well as the fact that there are more than 1 hydroxyl group. In this case, there are 2. So I got to use that prefix of diol. All right. So that kind of covers the 3 different scenarios that you're going to see about alcohols. You're going to see them either on the main chain by themselves. You might see them with a side group, another side group, not just the hydroxyl functional group. And sometimes you might see more than 1 hydroxyl functional group. So those are the 3 scenarios that I've given. Now, oh, the page that has all the mystery on it. See if you can pause the video right now and see if you can name all of these because they're not in the notes. You're going to have to listen to me to get your information. Pause me right now and then come back when you're ready. I'm going to walk you through all of these wonderful alcohols that are on this page. Okay. Do a little bit of cheating here. See, there's an iPad behind the other iPad. That's my secret. You didn't know that maybe. You probably did, but I just have to carry it. It's a little easier for me to do this. All right, let's give it a shot. 1, 2, 3, 4. All right, so I've got a molecule here that looks like that. All right, that's that one right over. I can't even point. I'm pointing to the wrong thing. I'm pointing right there. That's right. It's that one right there. Okay. So what have I got? Well, I'm going to count from this side because my hydroxyl group always want to be the smallest number. So that's going to be my number 1 carbon. 2, 3, 4, 5, 6. I got hexane. It's an alcohol because I got the hydroxyl group. So this is going to be hexanol. Hexanol, and I do have to indicate the position, pardon me. So it's going to be hexane 1-ol, and there is a methyl side group at the 2 position, so that's going to be 2-methyl hexanol. That's my first one. 2-methyl hexanol would be the first one on that, on the upper corner there. All right, let's take a look at another one here. Being very careful not to knock the board off its moorings. All right, so I've got 1, 2, 3, 4. And I got another position here, so it's 1, 2, 3, 4, 5. That is going to be a hydroxyl group there. And that is going to be 1, 2, 3, 4. Okay, so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. I got a non-name here. A non-name here. I'm going to count from this side, because that's going to give me the lowest number. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I got 10, pardon me. I can't count very well. That's 10. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a decane, pardon me. It's a decane. I've got my hydroxyl group is in a 1, 2, 3, 4, 5 position. So it's going to be decane 5-ol is going to be my main alcohol main chain. But I have a side chain, 1, 2, 3, 4. That's a butane or a butyl side chain at position 5. So it's going to be 5-butyl decane 5-ol would be that one right there. One in the middle, that's an easy one. That one in the middle is basically a gift because there's no side chain. There's only one hydroxyl group on that one. I've got 1, 2, 3, 4, 5, 6, 7, 8. But remember that last one does not count because that's the side chain or the functional group. So I got to count my carbons off from there. 1, 2, actually I'm going to start from this side, lowest number for the hydroxyl group. 1, 2, 3, 4, 5, 6, 7. I got 7 there. That is going to be heptanol. Because the hydroxyl group is in the 1 position, it's going to be heptane 1-ol. Heptane 1-ol, that's going to be this molecule right there. All right. Next one looks like a diol on the bottom left. There's a diol there. So I've got 1, 2, 3, 4. I got 1, 2, 3, 4, 5. It really doesn't matter which way I count this one from. I'm going to have positions 2 and 4. I've got 2 hydroxyl groups in there. So basically what we're looking at is it's going to be a 1, 2, 3, 4, 5. It's going to be a pentanol. But there's 2 of them. I have to indicate their position. 2, 4 diol. So this would be pentane 2,4-diol. Again, I got 2 hydroxyl groups. That's why I have the diol. And I've got position 1, 2, 3, 4, and 5. So it's going to be pentane 2,4-diol. And the last one looks ugly because it's not a skeletal. It is a structural formula. So it looks kind of ugly. I'm going to break this down to make it into a skeletal formula just to make my life a little easier. The hydrogens might throw you off, but again, we're going to ignore the hydrogens. So I've got 1, 2, 3, 4, 5, 6, 7, 8, and then I've got a hydroxyl group there, and I got a hydroxyl group there. So if I look at it that way, it looks way less daunting, even though it doesn't have that uniform shape of some of the other ones that you see on the page. This is strictly a single chain alkane with 2 hydroxyl groups on it. 1, 2, 3, 4, 5, 6, 7, 8. The main chain is octane. So it's going to be octane. I'm going to count from this side to give my hydroxyl groups the lowest number. They're going to be 3, 4 because I've got 2 of them at the 3 and the 4 position. And because I've got 2 of them, it's going to be diol. So it's going to be octane 3,4-diol. That's how you basically name each of those formulas that are on that page. Let's flip it now. I'm going to give you the name now, and I want you to write down the structure. So I'm giving you the name now of an alcohol. See if you can actually name give me a skeletal formula. I think on the page it says condensed structural formula. Give me a skeletal formula. It's way easier. Pause me right now. See if you can actually do this. We're going to do what we just did, but in reverse. See what you come up with. All right, here we go. Heptane 2-ol. I got a heptane main chain, so I got to have 7 carbons. 1, 2, 3, 4, 5, 6, 7. There's my heptane main chain. It says that my hydroxyl group is at the 2 position. So I could draw it here, or I could draw it there. It really doesn't matter because I could count from left to right or right to left. But I'm going to draw it from here just because I'm going left to right. So there it is. If you drew it over here, provided that that was the side you were counting from, either way that diagram would have been correct because you're obviously going to have to name it from the direction where it's the smallest number. So if you did put it over here, you got it right because you just have to, when you name it, you have to be able to make sure you know you're counting from left to right or right to left. But that's your first one, heptane 2-ol. Next one's a bugger. Oh, that one's ugly. Side chains galore. I got a non-name main chain. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There's my non-name main chain. My alcohol or my hydroxyl group is at the 3 position. So I'm going to go from left to right again. 1, 2, 3. There's my hydroxyl group at the 3 position. I've also got an ethyl group at 6. So 1, 2, 3, 4, 5, 6. There's an ethyl side chain here. So there's my ethyl group off the 6 carbon. And then I've got 2 methyl groups. I've got one at 5 and I've got one at 8. So there's my whole diagram. Here's my 2 methyl groups. There's my ethyl side chain, and there's my hydroxyl functional group that makes it that 6-ethyl, 3,8 dimethyl, nonane 3-ol. Horribly named, I know, but that's just, once you know the pattern, it actually makes a lot of sense. Last one is also a diol as well. It's a shorter one. Oops. It was going to happen eventually. As I mentioned before, live television, it's great. But I really need a bigger table. That's what I really need around here. That's all right. We're good. Okay. Let's try this one more time without knocking the table over. Here we go. I've got a pentane main group. Pentane 1,3-diol with a methyl group in there as well. 1, 2, 3, 4, 5. There's my pentane main chain. I've got a hydroxyl group at the 1 position, hence that line. Don't confuse that with a hexane group because that line indicates this is the functional group right there. That's where there can be some confusion with these diagrams. Because when you see that on an alkane, you would assume that's a carbon there, but because there's the OH on the end, you got to know that's a side chain at that point. Remember, if it's not indicated, it's a carbon, but if there's an indication at the end of the line, that's a functional group. I've got 2 of them. I've got one at 1. I've got one at 3. So here's 1, 2, 3. There's my other hydroxyl group, and I've got my methyl at my 4 position. There we go. That is my 3-methyl pentane 1,3-diol. Holy Toledo! Take a look. Watch the video. Our buddy's going to give us some clues on how to do some naming if I didn't make that, unfortunately, crystal clear for you. Take a watch. All right. A couple of things about alcohols you should also be aware of. They've got lots of uses. They were up on that whiteboard before that I already just took off. I was a little bit ahead of myself there. A couple of things they can be used for. Ethanol is quite common in solvents in food, paint, perfumes, as well as hand sanitizers. Methanol is used for cleaning supplies, antifreeze. It's highly toxic, causes blindness if ingested in large enough quantities. And we can also use alcohol. This is one that the government loves to talk about, the one that we can use alcohols as a fuel additive. You may have heard of ethanol injected fuels. There are some gasolines can have up to 15% ethanol content in them. There are some pros and some cons to using this type of gasoline. Ethanol is going to release less CO2 when it's burned under combustion reactions, and it's also produced from renewable sources. So we're using renewable sources to produce gasoline rather than using fossil fuels that are a non-renewable resource. The problem with ethanol is it produces less energy when it burns. So that does affect fuel consumption, power of the vehicle, overall efficiency. So there is a bit of a drawback, but you're kind of being a little bit greener by using the ethanol fuels if you in fact use them. As well, it reduces land that's available for growing food crops because we're using plants to get the ethanol from, and now we're using that crop area for making essentially gasoline or additives to gasoline. Okay, that's alcohol. Next group, carboxylic acids. Carboxylic acids are basically, they don't have a hydroxyl side group, or a functional group, they've got what's called a carboxyl functional group. If you've taken biology with me before, you may remember this. We talked about amino acids having a carboxyl group attached to the main carbon when you form an amino acid. But essentially, so amino acids do kind of fall into the category. They're kind of an oddball category, but they also are, they do have the characteristics of carboxylic acids in them. What is it? It's going to be a main chain alkene or alkyne with a carboxylic acid, which is a carbon molecule. By the way, that carbon does get counted as part of the main chain. So if I've got 4 carbons in the R group and this carbon here, I technically have 5 carbons in the main chain. That would be a pentane main chain or pentene or pentyne, depending if I had double or triple bonds. So that carbon now, even though it's part of the functional group, is technically counted as part of the main chain, so keep that in mind. So basically what you're looking for is not just a hydroxyl group, because it does have a hydroxyl group in there, but there's also going to be a double bonded oxygen atom as well. So that's going to be the difference between an alcohol and a carboxylic acid. Is on the same carbon that has the hydroxyl group, there's going to be an oxygen molecule as well, double bonded. And the other advantage is, unlike alcohols, this functional group only appears at the end of the chain, because it can't physically fit itself into the middle of the chain because there's already 1, 2, 3 bonding sites taken up by the carbon. If you put it on a middle carbon, there isn't enough bonding sites on either. If you bond it to the next neighboring 2 carbons, you'd have 5 bonding sites, and the carbon can only bond with 4. So the advantage of this one is you don't have to number it, because it's always going to be in the number 1 position. So you don't have to call it, ethane 1-oic acid, because it's always going to be in the 1 position. That's where the functional group is always going to be, and that's the side you count from. So wherever you find this group at the end of the molecule, you automatically know that's where you start counting your carbons from, regardless of where your side chains are, if there's any side chains present. What is it found in? Lots of things. It's found in sunscreen, vinegar, saturated fatty acids and butter, nutmeg, chocolate. When you think about carboxylic acids, think about things that smell really nice. Fragrances. This is what's used in a lot of things that have very aromatic flavor or scent to them. Don't get confused by the fact that there are aromatic hydrocarbons, because there are, but these are the ones that actually are generally associated with smell. They have very unique smells to them, like nutmeg does, like chocolate does, like sunscreen does, vinegar. They all have very unique scent profiles that are basically caused by these carboxylic acids that are in them. Let's take a look at an example of one. This is the one that's on your page. I've drawn it out as a skeletal diagram. We're dealing here with 1, 2, 3, 4, 5 carbons. Remember, I'm always going to count from where the carboxylic acid is, and in this case, you can see my double bond O and my OH group there beside it. So I know that's carbon 1. I've got a 5-carbon chain, so I've got essentially pentane. But what I'm going to do when I name that pentane as a carboxylic acid is I'm going to get rid of the E and replace it with OIC acid. So it's going to be pentanoic acid. Again, I don't have to name where the functional group is, because it's always going to be on carbon number 1, always. However, this one does have a side chain, so we do have to factor that in. I'm counting from here because that's my lowest number where my functional group is. So it's going to be the 2 position. It's a 1-carbon side chain. This is going to be 2-methyl pentanoic acid. Final answer. Take a look at the notes. It's all there. I just didn't pull it up on the screen in case you were following at home. You already had that up on your screen anyways. All right. Let's take a look at a couple more. Well, actually, here, I'm going to give you some time now to play around. Here's your page. Go through it. Pause me. See how many of those you can actually name. See how many of the names you can make into formulas. I'm going to basically wipe this board off. Hopefully it doesn't fall down on me again. And we're going to go through all of this in a couple of seconds. All right. I'm going to get rid of this as well, just so I have more room to play with. You know what? I'm going to get rid of all of it. That way I don't have to erase the board all the time. All right. Let's do some of this. First one. This one here is easy. That one right there. Maybe I'll give you the finger there. How about that one right there? That one's got 2 carbons on it. There's no side chains. So we know it's going to be ethane. Because it's not ethane, it's got that carboxylic group on it. That first one in the corner, very easy, is going to be ethanoic acid. That's this one right here. All right. Next one over here. This one's kind of goofy because it does have some side chains going on. But I've got essentially here, I've got my carboxylic acid group there. And they've drawn it kind of like that. Yeah, that's pretty much what they've drawn it as. This would be indicated as a 1-carbon, 2-carbon, 3-carbon. So that's going to be propanoic acid. But there are 2 side chains off the propanoic acid. One's there, one's there. There was no hydrogens indicated on that diagram, so you know those have got to be carbons. So this is going to be, this is the 1 position, 2 position. This is going to be 2,2-dimethyl propanoic acid. Okay. This is going to be 2,2-dimethylpropanoic acid. Again, 3 carbons in the main chain. That's how I get propane. Change it to propanoic. I've got my 2 side chains at the 2 position, which are both methyl groups, so it's 2,2-dimethyl. All right, that's how I get the name for that one there. Let's take a look at this one. This is a nice easy one as well. No side chains. Just count the carbons. 1, 2, 3, 4, 5, 6 of those. I got 6 carbons. Let me just confirm that. 1, 2, 3, 4, 5, 6. Yeah, I got 6 carbons. That's going to be hexane, and because it's got the carboxyl group at the end, we're going to change that from hexane to hexanoic acid. That's an easy one. Hexanoic acid. That was this one right here. This one up here, condensed formula. A little bit trickier, right? So I've got that one's a little tricky because I got a hydroxyl group off of it, but it's also an acid. So now what do I do? Well, in this case, the carboxylic acid is going to take precedent over the alcohol. That now gets named as just a hydroxyl side group. So this one here, you know what? I'm not even going to do this one because you're never going to get anything that hard. I'm not even going to go over that one. That one's a bit of a trick question, but in case you wanted to name it, 1, 2, 3, 4. I got 4 carbons, so it's going to be a butane main group. The precedence goes to the fact that it's a carboxylic acid, so it's going to be butanoic acid. I'm counting 1, 2, 3. 3 is where the hydroxyl group is, so it's going to be 3-hydroxyl butanoic acid. So 3-hydroxyl butanoic acid. That was a tough one because we didn't officially talk about that at all in any of my discussions. That's sort of kind of combining 2 of the groups together. I would never give you anything like that difficult on a test. Let's go to the next one though. This one is a little bit. This one is actually combining a carboxylic acid and the halogenated hydrocarbon, or the halogenated functional groups. So again, priority is going to go to my carboxylic acid group. I'm going to borrow my my iPad again because it makes my life a little easier. I've got 1, 2, 3, 4, 5. I've got my carboxylic acid over here, and I got a bromine group over here. So I've got 1, 2, 3, 4, 5. That's going to be pentane. So that's going to be pentanoic acid. Pentanoic acid. But I do have a bromo side chain, and that's at the 2 position. So it's going to be 2-bromo pentanoic acid. 2-bromo pentanoic acid. All right. The last diagram on that page is again it's a hydroxyl group attached to the carboxylic acid. I've got a main chain of 1, 2, 3. No, I've actually got a main chain. Yeah, I do have a main chain of 1, 2, 3. That's my hydroxyl group. Here's my carboxylic acid. There's my diagram. Remember, I don't want to get confused here. If I see a hydroxyl group attached with a double bonded oxygen, I know it's not an alcohol anymore. It's a carboxylic acid. Don't get confused. This would indicate by itself that it was just an alcohol. If I only saw those, then I know I got an alcohol. Because I've got this hydroxyl group with the double bonded oxygen, it's got to be a carboxylic acid. This is going to be a hydroxyl group, so this is going to be 1, 2. This is going to be 2-hydroxyl. And then the main chain is 1, 2, 3. That's going to be propanoic acid. Propanoic acid. So that's going to be 2-hydroxyl propanoic acid for this one right over here. The ones on the bottom there to name, just make the structural formulas from the names. Pretty straightforward stuff. I got octanoic acid. That's a pretty straightforward one. That's going to be an 8-chain. 1, 2, 3, 4, 5, 6, 7, 8. And I've got my carboxylic acid group on the end there. There's my octanoic acid up on the board. Next one has got a bunch of side chains on it. It's pentanoic acid, so it's going to be 1, 2, 3, 4, 5. Put my carboxylic acid group there. There it is. And then I'm going to count from 1, 2, 3 in this direction. I've got, the next one I've got is dihydroxyl. So it's going to be positions 1, 3, and 4. 1, 2, 3, 4. So that's what this one's going to look like. This is going to be 3, 4 dihydroxyl pentanoic acid. And the last one, oh man, this is the mother. This is the mother of all of them. This one here, this one really kind of sums up. If you know this one, then boy, you are flying in this unit. This one is decanoic acid. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on the main chain. I've got my, I'm going to put this one on this side now just because it's going to be easier for me to keep track of what's going on. Because I'm going to count these 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. I've got 5, 7 where my bromos are. So I've got a bromo here. And I got a bromo there at 7. I've got ethyl groups at 6 and 8. So I've got 1 ethyl, 2 ethyls there. I've got iodines at 2, 3, and 4. So those are going to be my iodines. And then I'm going to have tetramethyl. I'm going to have a methyl side group there at 2, 1 at 4, 1 at 6, and 1 at 8. It's a mess, but that's the molecule right there. If you're still not sure about it, check with me in class, but that is legit. All right, there you go. Those are carboxylic acids. Woo! Again, flavorful and smelling kind of molecules, these carboxylic acids. Generally, when you think of carboxylic acids, think about things that smell nice or that have a very a great fragrance to them. That's usually the indicator that we're dealing with a question about a carboxylic acid. Fragrance will usually be the giveaway to indicate that it's a carboxylic acid. All right, the last one. We're on to esters now, and then we're done. Esters are basically a carboxylic acid and an alcohol have a love child. Carboxylic acid and an alcohol are going to react together with each other, and they are going to create a functional group that is always going to be found somewhere in the middle of the molecule, and that functional group is going to be a carbon with a double bonded oxygen and a single bonded oxygen to it. It's going to be in the middle, so if you see something that looks like this on the end of the molecule with that hydroxyl group, you pretty much know you got a carboxylic acid. But if you see that kind of configuration in the middle of a molecule somewhere, now you want to start thinking it's an ester, because you're never going to find a carboxyl group in the middle of a carboxylic acid. You will always find this one buried somewhere in the middle of the molecule, because the one side of the molecule represents the part that was bonded to the single bonded oxygen molecule of the functional group. That part of the molecule was originally the alcohol. The R2 group was originally the alcohol that was involved in the reaction. The R group that's attached to the carbon, and again, just like carboxylic acids, this carbon has to be counted as part of the length of that chain. So if this is like, say, a 3-carbon R group, I'd have 1, 2, 3, 4. That now becomes a butane chain, not a propane chain. You have to count that C as part of the actual length of that chain. This oxygen then separates the length of that chain and however many carbons are over here, which I'll explain in a couple of seconds. You have to name this. This part of the molecule basically comes first, and this part of the molecule over here comes second when you name these substances. But again, getting back to this, the R2 group is originally the alcohol that's attached to the single bonded oxygen. The carbon that's attached up on the functional group to its respective side chain, or not to its side chain, the main chain attached to that carbon, that's originally going to be the carboxylic acid. So that's sort of what it looks like. And again, in the page on your data sheet, it's all there nicely explained on the actual generic formulas there on page number 9. So how does this all work? Well, you're going to name the ethanol group part first, and you're going to replace, if this was, let's say, ethane, it would become ethyl. So this is an ethanol group or an ethanol alcohol. It becomes ethyl when you name this ester. And then the second half of the name is the carboxylic acid. Let's say I had butanoic acid, 4 carbons, right? That butanoic acid now becomes butanoate. So we change oic acid to onate, or O8 is the ending of that. Actually, that is actually wrong. It says onate. That should just say O8. So oic acid becomes O8. Oat with an E on the end of it. Let's see how this all works out. So for example, Here's an example right here. Well, here's a bunch. I'm going to give you one right off the bat just to kind of help you out. All right. So the first one, let's do this one right here. I'll do this big one right here in the middle. So I'm going to draw that one out right now. I'm going to do one, and then I'll let you guys do some at home on your own. Okay. So I know this here originally was the alcohol, so we're going to start naming from that side first because it's attached to the oxygen. I know this has only 2 carbons on that alcohol. So originally that would have been ethanol. So we're going to change ethanol to ethyl. So this becomes ethyl. Pretty straightforward. This side now was originally the carboxylic acid. We're going to name it second. 1, 2, 3, 4 carbons there. That means it was butanoic acid. This now becomes ethyl butanoate. Ethyl butanoate. It's as simple as that. Name the alcohol group first, then the carboxylic acid. Replace ethanol with, or anol with YL as an ending, and the carboxylic acid group now becomes anoate, is what it ends as. All right. Pause me. Give me a couple of seconds, or give you a couple of seconds to try a couple of these out at home. See what happens. See what you can do. And then I will get back to this. Alrighty, let's see what you came up with. Let's start with this one right over here, okay? I've got, it looks like an ethyl, I got ethanoic acid. Sorry, not ethanoic acid. I've got ethanol on one side of that molecule. I can see that for sure. I'm going to reduce this down to a skeletal formula, which you can see right there. Technically, I wouldn't have to put that carbon in there because it is a skeletal diagram. There's my skeletal diagram of that molecule right there. What have I got? Well, I've got a single, I had methanol there originally. So that's going to become methyl. That part becomes methyl. That's this part here because that was originally my alcohol. Now this is my carboxylic acid over here. I got a 2-carbon carboxylic acid. So this is going to be methyl ethanoate. Methyl ethanoate. That's how you would name that one. All right. Let's take a look at this one over here. So on this side here, I've got 2 carbons on my alcohol, so that means I'm going to have ethanol, which means it's going to get reduced to ethyl. So this part of the molecule gets reduced down to ethyl because it was originally ethanol. Here I've got 1, 2, 3 carbons there. So that would have originally been propanoic acid. That's now going to be propanoate. So it's going to be ethyl propanoate for that molecule right there. Okay, I did that one already. Let's look at this one over here. The next skeletal diagram is going to be, like so. 1, 2, 3, 4. Okay, so again, I got to figure out which is my alcohol. My alcohol is always attached to my single oxygen molecule. That's going to be 2 over there. That means I've got ethyl, not ethanol anymore. It's ethyl because it was a 2-carbon alcohol. 1, 2, 3, 4. I've got 4 carbons that were originally on my carboxylic acid. That's going to be butanoic, which now becomes butanoate. So this one becomes ethyl butanoate. All right. Last 2 on the bottom are going to be condensed formulas. So I'm just going to go to my iPad and point them out to you here. It makes it a little easier than me drawing them. I've got 1, 2, 3 off the single bonded O. That means I've got propanol, which becomes propyl. Okay, so propyl is going to be my alcohol. Originally, what was my alcohol group in there because it's attached. Oh shoot! I went past the slide. I shouldn't have touched it, but I did. No big deal. We're back. Let's bring it back. having some technical difficulties here, folks. Let's try that. There we go. All right, let's go back to that one. I won't touch the screen this time. All right, so I've got this one right here. Propyl, I had this one right here. So 1, 2, 3, I had that one. So that's propyl. That was originally propanol because it had 3 carbons in the alcohol group. So that becomes propyl. On this side, I got 2. So I've got ethanoic acid, which becomes ethanoate. So this is a good way to kind of show you this as well. Some people think, oh yeah, when you name these, the larger chain has to be before or after the smaller chain. Doesn't matter. The first chain, the alcohol could be longer than the carboxylic acid or vice versa. Doesn't matter the length of the chains on either side of the ester functional group. What you want to be aware of is that you always name the alcohol before the carboxylic acid portion of the molecule. All right, and yeah, there you go. Give you a couple of examples there to work with. Hopefully that played out well for you. Okay. What are esters? What's the main thing about esters you should be familiar with? Plastics. They are what we deal with plastics all the time. Esters plastics are probably the most common group that we are familiar with that are esters. They're comprised of long repeating, they're repeating subunits, monomers that create these polymers. Take a watch. This video here will give you a little bit of information about plastics. Polyester is an example of an ester that can make everything from t-shirts to tow ropes. One of the biggest issues right now is obviously, how do we recycle plastics? And a lot of times plastics we think are getting recycled, but they're not. They're getting burned rather than actually being recycled. One of the trends now is going to what we call bioplastic. And bioplastics are organic polymers that are more easy to break down than these traditional esters. So that's basically, so when you think of esters, think plastics. When you think of carboxylic acids, think about things that smell, they have a very fragrant smell, vinegar or solvents and perfumes, the scent of a perfume or nutmeg or chocolate, and then alcohols would actually be the solvents that you would find, and also be like antifreeze, and they would be fuel additives as well. So you should be familiar with not just how to name them or how to identify them, but what they're sort of used for in day-to-day use in our Western society. Review right here, the functional groups. That was a really long video, but there was a lot to cover today, and there are some questions coming up. Here they are. You've got questions 18, 20, 21, and 23 on pages 266 to 273, and questions 1 to 4 on pages 277 and 278 of your Science 30 textbook. That's it for today. We're going to wrap up our conversation on chemistry and the environment next day when I discuss with you the fascinating topic of 2.3. And I'm not even going to tell you what it is, but you know where it is. It's right over, it's over here. It's over there. Click if you want to watch ahead. That's completely up to you. Take care.